Welcome everyone to today's PCS IBS seminar. It's a great pleasure to have with us Professor Romain Vasseur. And I would like to ask our scientific host, Dario, to introduce our speaker. Please, Dario.
Yes, thank you, Thielen. So it's a great pleasure to have today Romain from Massachusetts. Let me introduce a little bit his career. He got his PhD in 2013 from Saclay and École Normale Supérieure in Paris, with the thesis his advisor were Jasper Jacobsen and Hubert Saleur, and his thesis was about in decomposability in field theory and applications to disorderly systems and geometrical problems. After that, he moved for 4 years to Berkeley, where he was a postdoctor, and he worked in collaboration with Joel Moore. And finally, he moved to University of Massachusetts, where he remained, where he's still there, and is currently an associate professor in University of Massachusetts. Now, the research interests of Romain are quite diversified, but in general, I would say they are mostly focused on, entanglement and quantum many-body dynamics and similar topics. And today we'll talk about entanglement transitions. So please, Romain, is your moment.
All right, so thanks a lot for the introduction and for inviting me. It's a great pleasure to be giving this talk, even though it's online, and I hope I can visit the department in person in the near future. All right, so today I'd like to give you kind of a general talk on what on a topic or research that I've been pursuing for quite a few years now, which are entanglement transitions. And of course, in this talk, my goal will be to kind of explain what those are, right? What those transitions are, why I think they are interesting, and timely, and why it's kind of an exciting field right now. And hopefully I'll try to give you a flavor of what those transitions are. But in a nutshell, I'm going to be talking about some types of phase transitions in which quantum entanglement is really playing a key role, and that really occur in quantum many-body dynamics. Okay, and so if you're interested, I'm mostly going to be talking about the papers listed below. Those papers are like a couple years old, so they're not like, I'm mostly will try to give you kind of an overview. So I apologize if some of you have heard some of this stuff before. Before I start, let me thank my collaborators. So this is something I started a few years ago with Andrew Potter, who's now moving to UBC, Yezhuang Yu at UC San Diego, and Andreas Ludwig at UC Santa Barbara. And I'm also going to mention more recent works with Xiaoming Zhen at Cornell, my student Javier Lopez, and my postdoc Braden Ware, who's moving to Maryland soon. Okay, and so, all right, so let me start, and please do interrupt with any question or anything I can clarify. So let me try to kind of set the stage first, just to make sure, I'm going to have a fairly long introduction just to make sure we're all on the same page. So let me start by kind of explaining what my motivation here is, okay? So a large part of my research is about trying to find universal phenomena at high energy far from equilibrium, okay? And so, it may sound a bit surprising. So the word universality, usually you hear it, you learn about it like when you take your first course on phase transitions and critical phenomena. You learn about beautiful concepts of modern physics, of the renormalization group. You learn about scaling laws, near phase transitions. You learn about universality, right? The fact that some properties like critical exponents will not depend about details of your system, about chemical makeup or anything like this, and they will instead fall into broad universality classes, right? And when you learn about phase transitions, classical or quantum, you also learn that interesting universal phenomena happen at low energy or low temperature, right, and long distances. And so if you open like a textbook on quantum phase transition, say by Subir Sajdev or whatever textbook you like, typically you'll find the cartoon phase diagram that quantum condensed matter physicists like to think about. This is what a typical phase diagram would be like, right? You have a system, maybe at 0 temperature, there's a phase transition. There's a quantum phase transition that's driven by some parameter G here. And I'm imagining maybe I have an ordered phase, maybe it's a ferromagnet, an antiferromagnet, maybe it's a topological phase, depending on your, on what you like. And if you go to, this is a quantum phase transition that's driven by quantum fluctuations. And if you go to finite temperature, right, so if you crank up the energy scale in your system, this quantum critical point will broaden into some quantum critical regime. Maybe you can have a phase transition that's a classical phase transition that's driven by thermal fluctuations. But if you go to really, really high energy or really, really high temperature, the common knowledge would tell you over there, like in that regime. So first of all, there's not going to be a lot of quantum mechanics going on. And second, there's not a lot of universal that will happen, right? And you don't expect any big phase transitions or any universality in this regime. And so in this talk, I actually want to convince you that in some way, you can find quantum universal phenomena happening in this regime, but of course there will be a caveat. And the caveat will be mostly what I mean by this y-axis, okay? And instead of thinking of really temperature, we'll consider systems that are actually far from equilibrium, but still will be in this high energy regime. Okay, and so most of this talk is going to be really about the dynamics of isolated systems, okay? And I actually in this talk, I will also talk about systems that are open in some way. But mainly the most fundamental question, that I want to ask is whether those systems open more exotic alternatives to that scenario I just gave. And so this is largely motivated by many beautiful experimental developments in many different platforms. I'm not going to talk about in details, but the main common theme here is we have now many engineered systems, or maybe less engineered systems that can have very long coherence time. And when the typical condensed matter experiment is actually a bit different, right? So instead of having like a sample that's in equilibrium at a given temperature that you try to keep very low, the typical type of setup is now very different. And and the standard experiment, if you want, is more about thinking of quantum dynamics. So the idea is you'll have a Manybody quantum system. For this talk, it won't matter too much what it is. You can imagine you have a bunch of spins or electrons. I'm going to be thinking of, say, fermions on a lattice, say, and you prepare your system in some initial state that you can prepare, and then you let it evolve with time, and that's it. So it's a very simple setup, very general, okay? And crucially, there's no temperature here, there's no equilibrium. It's all about just having an initial state and following the laws of quantum mechanics, okay? And so you have unitary evolution, you just follow the Schrödinger equation, that's it, okay? So importantly, contrary to most, standard condensed matter like talks, you'll hear, I won't be thinking at all about the ground state or like about low energy physics. Instead, I will actually think of initial states that have, overlap with basically all many-body states in the spectrum of your Hamiltonian, meaning that the initial state will typically overlap with many states in the middle of the spectrum of your system. So this is here plotted as a cartoon of just a many-body spectrum of a typical Hamiltonian. So on the lattice, you take a spin chain, you diagonalize it. This is what it would look like. You have the energy, like the ground state is over there. But here we'll be thinking of states that are deep in the middle of the spectrum, right? And so if you remember your like thermodynamic classes, like, states over here, like if you think of equilibrium, they really correspond to infinite temperature, like very high temperature. Okay.
So in particular, your initial state will be volume law entanglement or area law?
So no, the initial state will actually be area law entanglement. I'm coming to that. But okay. Because it overlaps with all those systems, it will thermalize to a state that has volume law entanglement. So okay. I'm coming to this, but it will be highly entangled at long times. Okay. Yeah. So precisely, I'm coming to this. So I had entanglement in my title, so I'm going to be talking a lot about entanglement. So as I saw, you had talks on like dynamics and entanglement before, but let me just like go through a couple of definitions and just remind you of what the the basic definitions are. So I'm going to be thinking in universality and phase transitions in entanglement, right? So this is really what this talk is going to be about. And so precisely, I already answered this in this question. I'm going to be starting from a state that has that is typically, say, a product state. So say you have a spin chain in 1D, you have a bunch of spins, and you start from a product classical state. And as your time evolves, your system will get entangled. And a way to characterize this is to think that if you take, your system will always remain in a pure state because it's unitary quantum mechanics. You're not losing any information. You start in a wave function, pure state, you end up in a wave function. But if you think of local observables, like say I picture a subregion A of your system, and you ask about the local properties of your system here, correlators in that system are characterized by a reduced density matrix, right, where you trace out the rest of the system, A bar. And this can effectively become, it's going to be a mixed state in general. And at long times, most many-body quantum systems that we know of, and there are exceptions, will thermalize, that is to say, they will reach thermal equilibrium. So at long times, this reduced density matrix will approach some Gibbs distribution with some effective temperature that's set by the initial states only. Okay. So I'm not going to be talking too much about thermalization. It's a very deep topic. It's very interesting the way it happens, right? You start from unitary evolution. That's you don't lose any information, but somehow if you only think about local observables, they completely forget about the initial state, right? The memory of the initial state is kind of scrambled, if you want, into highly non-local degrees of freedom that you can never measure in your system. And so if you only measure local observables, all you see is just this effective temperature. You only see conserved quantities in your system. Okay, so this reduced density matrix, you can compute an entropy out of it. And as Dario was asking, this will be volume law entangled, meaning this entropy will now just coincide with the thermodynamic entropy, and it's extensive. Okay, so it will scale with the size of your interval, and so that's what we call volume law entanglement. How does it grow with time? Well, it's pretty well established by now. It was first, thought about, considered by Collaborators in the concept of field theories. But now we kind of know that for generic systems, the way entanglement grows with time is just linearly. So if you compute an entropy out of this reduced density matrix, which is called entanglement entropy, it's going to grow linearly with time, and then it saturates to something that scales with system size. Okay. So that's the generic behavior. That's how, it's a fairly universal behavior in itself. That's how entanglement behaves in typical many-body quantum systems. And when you have there's no proof of this, right? It's just based on the general expectation that many-body quantum system will just reach thermal equilibrium on their own, okay? And as the way they do this is that subsystems get highly entangled with the rest of the system. So even though there's no bath in the system, coupled to your system, if you want the rest, A bar is acting as a bath for A. Okay. So whenever you have a rule, it's always interesting to ask about counterexamples, right? And so part of the excitement in the community is to try to find examples where, for example, entanglement is going to grow a lot slower than this. And so you can ask, does it always happen that you grow, the entanglement grows linearly and you reach a volume law state? And there are exceptions. So one known exception is what's now known as many-body localization, and considering systems that have strong disorder. Okay, so it's a topic that's close to my heart. I work a lot on this, but I'm not going to talk about it really today. I just want to mention it in passing, because you might have heard about this at some point or another. So if you take spin systems or fermions and you add disorder, strong disorder in your system, it turns out that entanglement can grow a lot slower than linear. It can grow logarithmically. And if you think of the eigenstates of your system, so if you start here from a single eigenstate, it's not going to evolve with time. So based on this, it should have volume law entanglement. But in those systems, those eigenstates actually have area law entanglement. Okay, so there are exceptions. And so, in this talk is basically going to be about playing with those exceptions, or even more so, actually thinking about whether we can find systems in which we can tune a parameter and change the way entanglement is growing under dynamics. Okay, and so that's what I'm going to call entanglement transitions, which is now, I think, becoming a more or less standard term. for the type of transitions I'm going to tell you about. And so the typical setup I'm going to have in mind is, imagine I have a system in which now there's a parameter, I still call it G, that you can use to, again, tune the how entanglement is scaling in your system. Okay, so I imagine I have, like, if G is less than a critical value, maybe entanglement will grow linearly with time. Your system will become highly entangled, and it will maybe thermalize and reach volume law entanglement. But maybe if you crank up G above a critical threshold, you have a transition that I'm going to call entanglement transition, because really it's, entanglement is really the key quantity that's changing here, where, say, you will reach area low, then area low scaling of entanglement. Okay. And so you already see that in order to have this, really, you need your system to kind of not thermalize or not reach thermal equilibrium. So it will have to be like, pretty weird in some way. And I'll try to give you examples of such entanglement transitions. Okay.
Is it the standard situation in which is the strong coupling limit, which is not thermalizing?
Well, it depends on what you mean by coupling. I haven't specified what G is here. Right. So I'm going to show you examples in which G is going to be something very different. It's going to be either, say, disorder in your system, so it will be a bit similar to classes. Okay. Like, you can think of classical classes. So that's the example of Manybody localization. Later on is going to be maybe like measuring your system, and so in which case it's not fully closed. And then I'll give a couple of examples. Okay. So is there any other question before I move on? That's kind of the general stage, and that's what I'm going to mean by entanglement transition. And so the rest of the talk will be to try to just give you examples of what those, I'll try to convince you that those transitions exist and that they can have interesting properties. Okay.
Seems there's no questions.
Okay. That's fine. Let me keep going and just give you a couple of examples. So one example is of entanglement transition, and to my knowledge, I think it's the first one that was ever discovered, or it is something I already mentioned. It's the so-called Manybody localization transition. So again, I'm not going to talk about it too much today, but just to, again, give you the stage and what the claim is. The claim is, if you take an isolated quantum system, say a spin chain in 1D, Manybody, you have interactions. As a function of disorder, you can have a very different regime. You can either have your system that will reach thermal equilibrium. So you do this type of quench experiment where you start from some initial state, let's say a product state, and you let it evolve with time. And this system will thermalize, so it will forget about its initial condition. Everything you learn in textbooks is okay. You have statistical mechanics at long times. And from what I told you, you have volume law entanglement. Entanglement is growing very quickly in such systems. And the claim is that if you crank up disorder, so you have quench randomness, so imagine you have random magnetic fields, for example, in your system, local magnetic fields, you can get Manybody localization. And it's pretty much defined as the opposite of this. So, your system will retain some information of your initial states. Entanglement will grow very slowly, and you'll get, say, area low entangled, eigenstates. And so in the middle, there's a transition, which is known as the Manybody localization transition, which is very interesting in itself. There are many people, including myself, working very hard to understand that transition. It's a completely new type of transition, right? It's a type of entanglement transition that I'm defining here. It's not in equilibrium. It has nothing to do with ground state physics. It has nothing to do with, like, low temperature. It's really a dynamical phase transition. There's nothing going on in the ground state of the system at that point, right? So that's an example of an entanglement transition. So mostly in the rest of this talk, I'm going to be focusing on another example, which has attracted a lot of attention recently.
Sorry, maybe,
go ahead.
Before, a simple question. You say that is nothing that depends on the ground state, but also the ground state do the transition, right? It becomes area low versus volume low, or not?
No,
or is always area low?
No, that's right. The ground state is always area low entangled.
Correct. Okay.
Right. So yeah, no, like there's really, literally, if you just look at the ground state, it can be
right. You don't see anything. Yeah.
You really don't see anything. That's right.
Right. Okay. Thanks.
So you really have to be looking at the whole spectrum of states or
Correct.
dynamics to see it. Yeah.
Thanks.
Yeah. Very good. So yeah, like I said, I'm going to be focusing, I have to focus on one example for the rest of the talk. I'm going to be talking about what's now known as the so-called measurement-induced transition, which is another example of entanglement transitions, which I think is really, simple and very elegant in some way, or at least I found it very elegant the first time I learned about it. And so hopefully I will convince you that's another interesting example of such an entanglement transition. So let me tell you about the setup. So this was introduced in those two papers from a couple of years ago. So not by me, and so by first paper by Skinner, Ruman, and Nahum, and Lee, Chen, and Fisher. So if you're interested, you can have a look at those papers. So what is the main idea? Okay, so the main idea is to kind of have a competition, and to slow, if you want, the way entanglement is growing by actually interacting with your system, and the way you interact with it is by measuring it. Okay, so it goes a bit beyond what I said I would work with isolated quantum systems. So here, a system is not really isolated, like you actually effectively do something on it. You actually measure your system. And measurement is a weird operation in quantum mechanics, right? So it's we all learn when you learn quantum mechanics that measurements are projective, right? You have the wave function collapse, and it's effectively a non-unitary transformation, okay? And so what those authors introduced in a nutshell is an idea that you can use this competition to get a transition. So let me describe the model a little bit more. So for convenience of theory, and also to explain the model, we're going to be thinking of a specific type of, if you want, chaotic dynamics, or dynamics in which entanglement grows a lot, which are known as random unitary circuits. So those have been, very fashionable lately, and that they also realized in, say, the Google experiments. But they're also very convenient for theory. So those circuits are defined as follows. So instead of thinking of a Hamiltonian system, we can imagine we just have a bunch of, say, qubits or spins or d-dimensional systems. And the time evolution is given by this kind of brick wall pattern. Here, each rectangle is a unitary gate. So that is to say, it's just a unitary matrix acting on nearest neighbor spins. Okay, so if you have qubits, this is just a 4x4 unitary matrix. Okay. And those, so this is called the quantum circuits, where you just have a bunch of gates. Okay, so that's kind of operation you would do on, say, a quantum simulator, a quantum computer, right? So you just have the gates acting on spins. And those gates are actually chosen at random. Okay, so you take them to be random, and you take them to be random in space and in time. Okay. So that may seem to be a weird model to you if you're not used to this, right? So why would you do this? So the idea of those authors, Nahum, Vijay, and Ha, was, it's inspired by random matrix theory in some way. It's kind of a minimal model for quantum mechanics, for quantum dynamics. Okay, so why is it a minimal model? Well, you're only keeping a minimal number of ingredients. You have unitarity, so that's quantum mechanics, and you have local interactions. Okay, so the fact that it's local is because you have this brick wall pattern. So you see, the first spin only interact with its neighbor, okay, and then you have this brick wall pattern. You never have a gate that acts directly on spin 1 and spin 10, right? So you have short range kind of interactions, but there's no Hamiltonian, no energy, and so on. So those models are especially nice because you can do many things analytically with them, and hopefully I'll convince you of this by the end of this talk. And you can show many things analytically. For example, you can actually compute analytically entanglement growth and things like this in such systems. Okay, but again, there's no Hamiltonian and there's no conserved quantity here, for example, only quantum mechanics and so on. So it's kind of a minimal model of quantum chaos, if you want, of chaotic dynamics. Okay. So the second ingredient, so this is actually not crucial to the physics. It's mostly just for practical calculations. So crucial ingredient is going to be measurements. So I said I'm going to measure the system, okay? And I'm going to measure it locally. So here in that plot, whenever you have a black dot, it means that with some probability P, you will measure the states of that spin in the system. Okay. And so the basic idea is you have a competition here between the scrambling or chaotic dynamics of the unitary quantum circuit and those measurements that are effectively disentangling. So let me explain what it means. So as a function of P, you have a transition. So if P equals 0, you don't measure the system, you just have those unitary gates, and entanglement will grow a lot and you'll get volume law entanglement. If you increase P, the claim is you'll get one of those entanglement transitions, which again is known as measurement-induced transition. So one way you can convince yourself of this is if you take P to be large, say 1, right? So P equals 1 means that every single time you have a black dot, you measure the spin. Okay. So remember, it's quantum mechanics, right? So you take the first spin, you measure, maybe you find it's up, right? Let's say it's a spin 1/2, you find it's up along the z-axis, then the spin is actually going to be up, right? You have wave function collapse, so it's up. Then you measure the second spin, maybe it's down, and the third spin, maybe it's up. Okay, and so if you do this in every single spin, what you have at the end is just a classical product state, where the first spin is up, the second spin is down, and so on. Okay, so if you do this after you do the projection, you have wave function collapse on the classical product state, you have 0 entanglement left in your system. Yeah. Right, so the claim is that as a function, what those authors realized mostly, by simulating all those systems numerically, is that you get a transition as a function of this measurement rate P. Okay, and so this is a plot here from one of those early papers from Matthew Fisher's group. They're plotting entanglement entropy of half of the system in a steady state. So that is to say, they take a system, they wait for a very long time, they do this, they measure the system and so on, and they plot the entanglement entropy. Importantly, we're thinking of quantum trajectories here. That is to say, like, really, you measure a spin, you find it's up, then it's up, and your system is always in a pure state at all times. Okay, so you can define entanglement and you can measure it. And what they find numerically, I don't know if you can see the Scholar scale very well in that figure. So P equals 0, so this is a log-log scale. So it's actually, slope 1 here, it's Jove's volume law. As you crank up P, you see entanglement grows with subsystem size a lot slower. The black curve is supposed to be the critical one. And you see that if P is above a threshold, which is not that high, entanglement just reaches a constant with the sub size of the system. And that's area law entanglement. Okay. So this problem is, it's really intrinsic. It's only quantum mechanics, right? All you have is just unitary dynamics and measurements. So it's very fundamental and very simple at the same time. And it has, over the years, people realize you have beautiful relations to, say, quantum error correction, which I'm not going to talk about too much. But
sorry, I'm not getting very well what is A in this. I mean, the total number of spin is 512, am I right? Always.
Yeah, so I should say, okay, so you could be surprised that they can do numerics with that many spins. So they're using Clifford circuits, which you can simulate classically. So that's how they can reach big systems.
Okay, no, but the question is, so A is the dimension, you do a bipartition in which you take A and L minus A.
Correct.
Okay. Okay.
Yes, sorry, yes, absolutely. So you take a subsystem, so they take a big system of 500, and then they take a subsystem of size A, and you see how entanglement scales in a steady state. So they also have plots of dynamics as a function of time. Here I'm showing at long times, and both kind of look similar.
Okay.
If you did it just with time, it would kind of look at the same, basically, actually, like it's yeah.
Okay, and how you said the black curve is the critical one. How you characterize?
Oh yeah, I just I'm going to show more precise plots. I mean, it may not be obvious. Like the critical one happens to be the critical one. The black one happens to be the critical one. Sorry, you can see that here it saturates, but maybe you could imagine the black one is also going to saturate, right? But yeah, and it's getting close to the full system size here as well, right? So yeah. I'll show more precise, like numerics for sure. Yeah. So this problem, like I said, let me just briefly mention the connection to error correction. So you can imagine that if you want, the unitary gates are kind of like hiding the quantum information or scrambling the quantum information in a way that the local measurements cannot access if you want. So you can think of the local measurements as kind of noise on your system, right? So you can think of the effect of the environment as measuring, by accident, if you want, some spins. And so anyway, this transition has to do with, if you want, the capacity of your quantum circuit to store some quantum information. And so because of this, it has attracted a lot of attention from many different communities. I'm just mentioning a few different works that have, there's literally, I think, close to, I don't want to count papers, but there's really many papers on that problem by now since those original ones. And I'm not going to talk about everything. Mostly what I'm going to tell you about for the rest of the talk is to give you some ideas of how we can understand this from the theory point of view by not doing numerics, but try to really come up with a theory of those transitions. Okay, so that's mostly what I've been doing on those problems. But many different people have been thinking about this model and more realistic models. Like if you don't like random circuits, you can throw them away, take a Bose-Harbert model and also do those measurements and find the same transition. If you don't like entanglement entropy, well, this is kind of a bad talk for you, but you can think of more physical observables that are scalable, they can realize in experiments. This was done by Michael Gerlens and David Hughes. And there are really many variants by now. And so this slide is even not that recent. And there's literally been dozens and dozens of variants and developments of that problem. I'm actually going to skip this. So there are different versions of entanglement transitions. And I was going to mention one related to tensor networks, but let me skip that and just focus on that measurement transition. So this is more precise numerics, right? So related to how do we know what the transition is? So let me tell you a bit more about that transition. So that's still from those original papers. So here, that's from the paper by Lee, Chen, and Fisher. And so what they did is really tried, they saw that transition numerically, right? And so they started to analyze it in the same way you would analyze a classical phase transition, right? Or something you would find in the ground state. So what they are computing, just to be very precise, so they're computing entanglement entropies or Rényi entropies, which are defined in this way. And they're averaging those quantities over those random circuits over where you put the measurements. So remember, the measurements occur at random, right, with some probability. And also you get the random measurement outcomes, right, because it's quantum mechanics. And, what you get at the end of the measurement is also random. But still, and so they look at this quantity entanglement and they find that it really behaves in a critical way. So what you see here, for example, is a type of finite size scaling collapse, which is similar to what you would find in more traditional phase transitions, right? So I just to give you a bit of detail, this is entanglement minus some value at criticality and rescaled by some exponent nu, right? So this type of finite size scaling you would get for a second order phase transition. And so out of this, what they managed to find is to extract are some critical exponents, right? And so that's the claim of universality, going back to my very first slide. Okay, so in a system, we're very far away from the ground state, we're just doing dynamics, thinking of entanglement. There's no low energy physics anywhere inside here. And yet you seem to find dynamic critical exponents, and they don't depend, they're universal in the sense that they don't depend on many details of what I told you about. If you don't like quantum circuits, you can change the model. If you, instead of qubits, you can take 3-state spins, you can change many things in the system and those exponents will not change. Okay. And so, for example, there's a correlation length exponent, which numerically is close to 1.3. There's a dynamical exponent that's near 1. Actually, it's exactly 1, and I'll tell you why. So z equals 1 tells you that space and time scale in the same way in this problem, which is a bit surprising because if you actually look at the problem, space and time are completely different, right? There's quantum mechanics doing measurements and there's physical space. But here it tells you, if you want, there's emergent relativistic invariance in this system, and even more than this, it turns out there's conformal invariance at this critical point. Okay, so this was shown numerically by looking at this quantity called mutual information. If you take two intervals A and B with, that in principle you have 4 positions, x1, x2, x3, x4 to characterize those intervals. And what they found numerically is that this quantity only depends on one quantity called cross ratio. And so this is known to be a probe to establish conformal invariance numerically, right? So it's well known in classical critical phenomena like percolation, Ising model, or things like this. So this is kind of a local version of scale invariance, right? So that's what you expect in more traditional, like, you know, so you have this whole conformal invariance emerging here, even though, again, there's really no reason to expect it far from equilibrium here, okay? So all of this is numerical observation. And so I, you know, at the time, my collaborators and I were really thinking about, okay, how can we try to understand this problem, like from a theory point of view, right? So what do you do as condensed matter physicists? We're mostly trained to deal with, again, ground state problems. And of course, we can try to use numerical techniques, but if you try to really use like theory techniques, you know, you learn field theory and things like this, right? And none of those seem very, like, you know, very like appropriate for this problem here, right? So how can you analyze this transition? It's pretty hard because entanglement is hard to compute. On top of it, you're doing those measurements and everything seems very non-linear, right? So because you make measurements, again, projective measurements mean that you measure the system, you get a new wave function that's projected, you have to normalize it again, right? That's how making measurements is doing, right? So you have to, you lose some weights, and intrinsically everything seems very nonlinear. So we want to compute some entanglement entropy, average over hard gates, measurement locations, and measurement outcomes, okay? So let me formalize this a little bit to tell you what you want to compute, and I just want to give you a brief of flavor of what the theory is like. I won't go into too much details, not to bore you. And so what you want to compute is something like this. So you want to compute Rényi entropy, okay, of a system of those things. You want to average it over like those circuits. So what I call circuits are those different random gates and so on. I'm dividing by trace of rho because my density matrix is not normalized because you're making all those projective measurements. So you lose some, you know, your wave function is not normalized. So you have to normalize it in the end to compute entanglement entropy. One crucial point is that this is quantum mechanics, meaning the outcome of a measurement depends on the state itself, right? So you have the so-called Born rules that tell you what you get at the outcome of a measurement, right? So like say if you measure a spin, you find it's up, the probability for it to be up is the overlap of your wave function squared with the up states, right? So that's like the usual laws of like what you get in quantum mechanics, and those are called the Born rules. And here they tell you if you take a circuit like this and you have a bunch of, you know, like in the red dots here are where you're making the measurements, right? So you have, this is a given realization where you had measurement in those places. And let's say this spin here, you measured it to be up, this spin here, you measured it to be down, and so on. You can ask what is, you know, you get a wave function in the end, which is not normalized. And you can ask what is the probability that this outcome happened? Well, it turns out it's exactly the norm of your wave function. And so that's trace of rho here, okay? And so what you want to compute is like this Rényi entropy weighted by those, you know, like average over all those measurements outcome with those probability of the Born rule, okay? So this is already formalizing the problem in terms of equations, right? So this is not the too hard part. You just have to think about what, you know, you have to remind yourself what measurements mean in mechanics and so, in quantum mechanics and so on. The hard part is computing this. And so the key like ingredient that we've been using is a so-called replica trick, right? So we want to average a log. And usually in physics, when you want to average a log, it can be convenient to use a formula like this one, which is just exact, right? That is, you just replace the log by this. And, you know, like here, m is a real number, but the key point is like this quantity on the right-hand side, it can be easier to compute its average if n and m are integers. Okay, so it's a standard trick that you use in disordered systems, in spin glasses, and so on, right? So you just replace the log by a formula like that, and you hope to compute the average of the quantity on the right-hand side, where m and n are integers. And at the end of the day, you hope to do an analytic continuation, right, where you take this parameter m to go to 0 and to get an answer in the end. Yeah. So that's the basic approach I'm going to take. So here n is the so-called Rényi index, right? So that's that's the parameter that enters, that enters this just definition of this linear entropy. M is this replica index that I introduced by hand. Okay. And so the claim is that for N and M that are integer, averaging a quantity like this over all those random gates and so on is something that you can do. Okay, so I'm not going to go into the details. It involves like how averaging what's known as one garden calculus. So, but there's a whole math framework to do this. Okay. And it turns out that if you do this, you can map the calculation of this whole thing onto a classical partition function. Okay. So you get a 2D classical statistical mechanics model, which is defined basically on the circuit. So the basic idea that you can have is it's almost like having Wick's theorem if you want. So you have a bunch of replicas, and imagine you had like Gaussian tensors. If you average over them, you would have something like Wick's theorem where you have to pair the replicas in order to get non-zero. The thing is, unitaries are a bit more complicated than Gaussian tensors. Okay, there's some direction of time and so on. And because of this, the formulas are a bit more complicated. But summing over those different ways of pairing basically gives you the statistical mechanics model. And so the statistical mechanics model is defined so that the spins, the effective degrees of freedom, if you want, are permutations. So it gives a relatively formal mapping, but it gives a very simple picture, which is like why I like to tell this story. So I won't go into any of the technicality. You can average those quantities like this, and it maps onto an exact classical StatMech model. Okay. And at the very end of the day of this mapping, which is pretty formal, and you get that something like entanglement entropy, which is something non-equilibrium in a quantum system, you can map it through the price of this replicatric as something which is a lot more intuitive, which has to do with just a spin system, like a classical system, like think of an Ising model, right? Classical Ising model in 2D. And entanglement ends up being related to like the free energy cost of creating a domain wall. And so that's going to be the main picture I want to emphasize, and which is really the main outcome of this whole approach. So this is a picture I'm stealing from a paper, concurrent paper that happened at the same time. They have a nicer picture than us. So they have a very nice picture illustrating this. So by Ehud Altman and collaborators. So the basic idea is as follows. So you have a StatMech model. Let's pretend it's an Ising model. It's not exactly Ising. It's a bit more complicated than this. And so this Ising model can have different phases, right? So it can be ordered, it can be a ferromagnet, or it can be a paramagnet. And it turns out that which phase you're in is tuned by this parameter P, okay? And this transition here, right, the ordering transition is actually going to be this entanglement transition. Okay, so there's a nice mapping between, so you relate those weird entanglement transition to something which is basically almost an Ising transition. And the claim is that entanglement is related to the free energy cost of creating a domain wall at a boundary. So what I mean by this is what you see on the picture. You imagine, say you have a ferromagnet, all spins are up at the boundary, but on that region A, you force the spins to be down. Right, and so you create a domain wall here, where the spin, the ferromagnetic couplings are unhappy, right? And so the free energy cost to do this is going to scale with the size of the interval here in that ferromagnetic phase. But now if you go to the paramagnetic phase, the free energy cost of creating a domain wall doesn't scale with the size of the interval, okay? Because it's a domain wall condensate basically already. So you only need, this is going to scale with like, the correlation length of your system. So this is volume law entanglement. This is area law entanglement. Okay, so really this is like, forget the replica. I had a couple of more technical slides on this replica trick and so on, but the claim is that this is kind of the qualitative picture we're getting out of this. We're basically understanding those entanglement transitions now as like the so-called free energy domain of a domain wall. And this has become a pretty qualitative picture to understand what entanglement does in those systems. Okay, so if you don't have a lot of measurements, entanglement is like a membrane or domain wall that goes through an ordered spin systems, like an Ising system. And if you have a lot of measurements, your StatMech model becomes disordered, like a paramagnet, and entanglement is now scaling as area law. Okay. So we can use this to get a lot of mileage, basically, because like we don't know a lot about entanglement transitions, but we know a lot about Ising models, right? Or about domain walls and things like this. And so now we mapped something like an entanglement transition onto some simple ordering transition in 2D.
Sorry,
and so
question?
there's a lot we can get out of this. Yes, sorry.
I mean, this mapping between, let's say, an entanglement transition and some, let's say, Ising transition after the replica trick, how much is robust against, let's say, changing the model? I mean, suppose that you start to remove the randomness in the unitaries, or I mean.
No, so that's a very good point. It relies a lot on the model, actually, right? So this is highly dependent on having really a hard secret and so on. However, we're counting on universality, right, to hope that what we get from that StatMech model is going to tell us about just more general cases where we kind of do the calculation, right?
Okay, but I mean, I understand that, you know, in order to extract a quantitative result, this is highly dependent on but suppose that I change the model. Do you think that still I will map an entanglement problem to a classical, let's say, Ising problem or not?
So if you change, say, the gates, you can still map it to a different statistical mechanics model. So,
I see.
So if you change if you change some details, yes, but if you change too much, no. So there's a threshold. So if you change just the family of randomness or which gates you choose and so on, you can still do some of the calculation. But I need some randomness to average over, actually, and so this helps a lot.
And I believe that also is quite crucial, the fact that your circuit is local, right? I mean, if you start to add non-local interaction, you break this analogy, right?
That's right. I mean, the StatMech model can be generalized in that case still. So it's a the nice thing is that it's very general. This whole mapping that I didn't go through the detail, it really, you can do it in higher dimensions too, and so on. So it's just like the question is, how much can you extract from it? Because the key thing I'm ignoring is this replica trick so far, right? So I see there's another question.
Yes, we have a question from Alexei. Please, Alexei.
Yeah, a follow-up to question by Dario. So how far can you change the model? So far you were talking basically about Ising model. Can you have more complicated models? So leading to not aerial controls, but I could imagine saying spin glasses, I think creating a domain wall scales with a different power of the system size in case the line segment. So my question is, can you do that? And second thing is, if you then try to reverse the mapping, what would be the original circuit model? Or perhaps even if you can predict what would be more physical models in that case.
I see. Okay, so those are two very good questions. Thank you. So let me say, okay, so I'm illustrating here saying it's an Ising model. I should be very careful that it's very much not an Ising model. So like the spins, actually, they live in this permutation group. So it's kind of a weird thing. And the Boltzmann weights are in general very complicated. However, the qualitative physics is this just a ferromagnet-paramagnet transition. So that's the first thing. And so this depends on the replica number 2. So most of the qualitative physics is given by, if you want, this Ising model, but really I don't want to give the impression that the StatMech model is only this Ising model. It's quite more complicated. So the question is, can we change the StatMech model and can we reverse engineering? Yes and no. Like we know how to play with like the details, like I was mentioning to Dario, with the gates and maybe change some of the Boltzmann weights if you want. I unfortunately do not know how to do the reverse engineering. So you're also asking about spin glasses. So one thing I should say, once I do this mapping, there's no more randomness. So it's one thing about that. The StatMech model is translation invariant, if you want. So it will just be, this phase is a normal ferromagnet. It's not a spin glass or anything like this.
Yeah, well, I mentioned the spin glass just as an example where the main wall price is something different.
So you could imagine now like making maybe those parameters P, you know, some of the parameter, like I have this parameter P, now I can maybe make it random and spatially non-uniform, and then maybe I could get a spin glass.
Well, I really meant that, I mean, again, spin glass was just the first example that came to my mind. I was thinking that, I mean, there could be other StatMech models, translational invariant, where perhaps the main wall cost doesn't scale as a simple linear power, but the difference.
I see. Yeah, so like all transitions we've seen so far are just ferromagnetic to paramagnetic transition where there's no exotic scaling. But yes, you could indeed use this as a way. So now you have this mapping. You can imagine, like you say, retro-engineering a bit, but it hasn't been done. That's a very good question, where you could imagine like maybe at least you could take the StatMech model maybe on a different lattice to modify parameters so that maybe you'll get different scaling. And that would give you more exotic entanglement scalings. So
yeah,
if
sorry.
that's your question, yes, it's a very good. I think it's actually something we are thinking about, maybe not exactly in the way you're phrasing it, but like to kind of use those StatMech models to get more like exotic or different entanglement scalings out of it.
Yeah, and sorry if I can ask one more question.
Yeah,
This is more related to higher dimension models, because I could imagine again, perhaps in this case, in the 1D case, you're probably getting the StatMech model is living on a relatively simple lattice, but in higher dimensions, you also map on a model that can live on different types of lattices, and in particular the ones that have frustration. And then again, I would expect that there something different might happen.
It could be. So this hasn't been explored at all yet. So far, I should say, like all couplings are ferromagnetic, so there's no frustration, at least in the, but again, that's with the parameters we've taken so far. There's maybe ways to modify the microscopic and the circuit, so maybe you could get frustration indeed, and that could have very interesting consequences for entanglement. Absolutely, yeah. So okay. It's still, I should say, it's a very recent field, right? I mean, those papers are like from last year. There's still, there's really a lot to explore for sure.
Okay. Yeah. Thanks.
Yeah. Thanks a lot. So I'm kind of out of time, so let me just like conclude. I'm basically done anyway, so that was mostly to tell you about this transition. Let me tell you that with the StatMech mapping, we can get a lot of things. We can get that, for example, entanglement scales look as a log at criticality. We can explain why you have conformal invariance and why this mutual information, I said that it's scaled that we know with some cross ratio and so on. We can explain that as well. So we can explain a lot of things about scaling from it. You may be a bit frustrated that I never wrote the StatMech model, and I'm just going to write it like this is my last slide in one limit. If there's one limit in which it really becomes simple and we can actually be more quantitative and get exponents and so on. It's in the limit where the on-site Hilbert space is very large. So here I was saying, oh, you have a qubit, right? Like a two-state level system. Now imagine you have D level and you take D to be very large. So this is kind of like a large N limit. In that limit, the StatMech model I told you about, it ends up being very simple. It's I'm able to write the partition function on one slide, and it's just given by this. Okay. And so if you know a bit StatMech models, this is a Potts model. This is a so-called Potts model. And the Potts model is very well studied, and we know how to take replica, how to analytically continue it. And in that replica limit, it maps just onto classical percolation. And maybe that's a fairly intuitive thing, right? So if you think of the measurements, it sounds like a percolation type problem, right? When you measure, maybe you disconnect the system. It sounds very like percolation, right? And so this is kind of what this mapping is telling you here in that limit. It does end up being just classical percolation. So if you measure, you disconnect your system. If you don't measure, you don't, right? So you can think of those as like cluster of not measured, of states that haven't been measured. And classical percolations, of course, we know the critical exponents. We can compute like all sorts of prefactor and so on. But in general, if you go away from this limit, it's not percolation anymore, and it's a big open question to understand the transition. Okay.
Is it?
And so that was just
this situation simpler
yeah.
because somehow when you go to the large D limit, also the entanglement part is becoming classical in a sense?
Yeah, I mean, in some way, yes. Here, I'm killing all quantum fluctuations in like a field theory way. Like it's really a large N limit in many ways. Yeah, and it becomes classical.
Okay.
And
so essentially,
to what extent
classical to classical mapping in a sense?
Yeah, that's right. I think it is like to a lot of yeah. In some way, I mean, it's an interesting but kind of like very special limit. And in fact, we know that adding 1/d corrections completely destroys this right away.
Oh,
so if you want the full transition is really a quantum percolation. It's like a quantum Hall transition if you want. It's not like a classical percolation for sure.
But do you still have a control over the 1/d correction? or
no.
become immediately?
No. So that's the problem. It's a relevant perturbation. So that's something I just had in the slide and I'm skipping here. But like we know if you want this, like one of the correction is relevant, and we have no idea. So that's what I was. So this is my conclusion slide, and so basically that was going to be my main conclusion. So I hope I convince you that you have new type of entanglement transitions and they are exciting. I just try to focus on a single example, mostly those like measurement transitions, where I briefly sketched this idea that we have those mapping onto things we know a bit better, like classical StatMech models. Those mappings give you a handle, we can write field theories for them. And so we know how to deal with them a bit more, right? But still it's very hard because of this replica trick. So this is going back to your question. We know how to deal with this replica trick only in this large D limit. But like you said, it's kind of a classical to classical model in some way. So it is a very special limit. The minute we add a perturbation, we can write field theories for it, and we know it's a relevant perturbation, and we have no idea what it flows to if you want. And the type of, what this transitions are defined, they're described by conformal field theories. And you can think that, we know those things pretty well. There are textbooks and so on, but like this class of conformal field theories are very complicated and nasty. So that's, they're actually related to things I did in my PhD. So I kind of went full circle on this. And so there are many, many open questions. And like I said, there are many exciting developments. Every week on Archive, there's something coming out related to this. And there's been a lot of excitement and exciting developments in many directions, both about the universality of this transition, about variance. And I think we even mentioned there's a lot of things in higher G, and and we can retro-engineer this to really get new transitions out of this. Can we classify and understand those transitions? So with this, I'm just going to stop, and thank you very much for your attention and the questions. Thank you.
Thank you, Professor Vasseur, for your excellent talk. Let's thank our speaker. Okay. So some technical issues. Okay, so please, questions. Oh, it's delayed. So until people wake up, and maybe let me start just a quick question. So you mentioned here experiments. So are there any kind of ideas or proposals for experiments? I think that second Rényi entropy can be measured, right?
Yeah, that's right. So let me say a few things here. So there is an experiment that's not out yet from Chris Monroe's group. So there are results, and they gave talks on this, so it's not top secret as far as I know. And so it requires a bit changing the setup of what I've been talking about. So one issue is that measuring entanglement entropy is hard. As you measured, okay, you can do like the second Rényi. But here on top of it, because you're doing like measurements on top of it, it requires a lot of post-selection and things that, in principle, if you really wanted to compute that quantity I'm describing, it would be like extremely unscalable. However, there have been proposals. Okay, I'm not going to go back in my slides, but there have been proposals in particular by Michael Collins and David Hughes of finding other observables that are scalable. So it turns out you can seed this transition by adding only a local probe, like an ancilla qubit that you couple to your system. And that's actually enough. You can just measure the magnetization of these qubits, and that's enough to see the transition. So actually, even though I presented everything through the lens of entanglement, you can get the physics of this transition without measuring entanglement entropy. You don't need entanglement entropy. So
the ancilla in this case is just connected to one qubit, or you need many of them?
The basic idea is you introduce, like at a given time in your circuit, you introduce an ancilla and you entangle it with a given spin in your system. And then you measure entanglement, but that's easier because a single spin. you would just measure like entanglement of that reference qubit. And that you can do, right? Because it's a single spin. And so this you can do in experiments. And so this is what's done. So basically you need something that's a bit less nasty than entanglement entropy. So that's one way, and that doesn't require post-selection or anything like this. So there are, okay, so, you know, up to now, it's not like, yeah, as far as I know, there's this one setup, you know, where like there are results, and it's kind of a variant with like, I think it's an all-to-all model where you have more interactions. You know, it's not like the 1D setup I'm describing here. So it's a variant of what I've been describing. But yes, you can, like I said, it is connected to some problems of quantum error correction in some way. So if you want, you can relate this transition to things that are like more like grounded in real life. Even though this is a nice setup, just conceptually.
Okay, thank you. We have a question from Alexei.
Yeah, well, actually several questions. So one thing, could you remind again where the log? So I mean, the difficult part in the mapping is using the replica trick to avoid the log.
Yeah.
So I just want to be sure. So the log shows up because you want the renew entropy. Is that?
Yeah, it's a bit more. Yeah, it's a bit more fundamental than this, because you could say, so yeah, indeed, I want renew entropy and I want to average this log. But you could say, okay, maybe I don't care about the log. Maybe I average trace of rho a to the n, and that's called purity, right? If n is 2, and maybe I'm happy with this. But this is still hard because rho a needs to be normalized. So because you're doing measurements, right? You're losing weights.
Yeah, okay.
So meaning that rho needs to be normalized. So if you want the more accurate formula is this. You need to average log of this ratio. But even if you remove the log, you still have a ratio to average over, right? So this is like in statistical mechanics. It's, you know, this is why you need the replica trick. The fact that you have a ratio, you have the denominator here. You know, even if you remove the log, it's still hard.
Yeah, right. That's what I was. What about the? I mean, this is a very naive question, but basically the only alternative to the replica trick I'm familiar with is supersymmetry. Is there anything? Yes. Is there anything like that here?
Mm-hmm. I thought about this. I wish I you know couldn't find a way to formulate it. Like, so supersymmetry is typically formulated right for non-interacting disordered systems. Like and there might be a way that, but we haven't figured it out. No. So here in the way, you know, in the way we introduce it, it's a bit straightforward. Supersymmetry would require writing this as some type of like Gaussian integral, right?
Well, actually,
yeah.
Mm-hmm. Yeah, well,
I mean, maybe there's a way I just don't know of. I did think it. I thought about this question a little bit. I didn't find a good answer. So if you have any idea of how to do this, I think that would be really nice.
No, I mean, I guess so long as it's interacting, I mean, supersymmetry really relies on the non-interacting one. But that reminded me this yet another trick that, I mean, basically whenever you need to average over disorder, I recall there's a third one, the Keldysh formula.
Keldysh, yeah, absolutely.
That one should work for the interacting systems. But so what about that?
Yeah, that's great. So the only thing is I don't really, I mean, it's not, you know, the typical quantity you would compute like in a Keldysh contour or anything like this, right? So because of the circuit, but maybe so this one I have thought less about because I'm also less familiar. I mean, I know the supersymmetry trick a bit more than I do Keldysh. So yeah, the key idea is like, can you formulate something like this, right? But you know, you have to do the partial trace. You have to do things like this, which I don't know how I would do, like in a Keldysh way, at least.
Okay, well, I mean, at this point, these were really wild guesses. I was just throwing up the methods.
No, I mean, I understand. Those are very natural questions, and like I said, I those have been asking myself, at least the supersymmetry one. Just the replica trick is natural, just because you have log and there's nothing else, right? Both supersymmetry and Keldysh use more specific setups, right, that we're familiar with in Manybody quantum physics. And here it's hard to, for me at least, to make them work for like this problem at hand, right, where we, you know, you just want to compute entanglements. like there is time evolution still hidden in there, right? Like, but really the issue at hand is more like this non-linearity all over the place. And I don't know how to use something else than replica. But yeah, it would be good because the replica trick has issues coming with it, right? So it would be great if we found a way to avoid it for sure.
Well, at least this would give a method to check the predictions of the replica method.
Yeah, yeah, no, absolutely.
Yeah. Anyway, I had further question is, so getting back to the mapping. So this works for the specific model, and that's what Dario has already been asking. But I'm just wondering, can you still, using this mapping, guess how, well, in some sense, does this mapping help to understand what you need to do, or what perhaps could be a theory for the more complicated models? So for instance, you mentioned the Hubbard model, where I guess this mapping simply doesn't work because it's not a unitary circuit.
Yeah.
So does it still provide like an insight how you could, what kind of a replacement, say for RG, you would need to develop for these more complicated, more realistic models?
Good. So that's it. Yeah, it's a tricky question. So in some way we can, like I said, we can modify the circuits a lot. And, you know, from the point of view of the StatMech model, you don't change the symmetry, right?
Mm-hmm.
So like, and you see like this type of transition is kind of replica symmetry breaking, right? So the thing that you're breaking here is kind of the replica symmetry of the model. So the way we derive the model, we need something to average over. So we need those gates and so on. And so like you say, if we take like Bose Hubbard model, truncate it in some way, we don't know how to do this. However, the hope, and like it's maybe more of a hope for the more realistic model, right? But is again, even though we don't know at all how to derive a StatMech model, and there may not be one, you still have this kind of replica symmetry, which is kind of actually physical. It's about permutating the legs of your density matrix when you take moments of it. That is continuously broken, right? So we hope the transition, if you want, is in the same universality class. And at least numerically, there's a lot of evidence that you can change the model a lot and you'll still get the same transition. So I think of the Haar random circuit as just a way to access that more realistic transition. But of course, it's conjecture since we don't really know how to, like, you know, do anything else than numerics in the other cases, right?
Yeah, but on the other hand, one might wonder whether perhaps there's something similar to the standard RG procedure where the quantum circuits, sorry, the unitary circuits is like the minimal model. And so to some extent, you would want to truncate or do some transformations in the Bose-Hubbard that would effectively map it onto the unitary circuits. So
yeah, that would be great. I think we even, like, you know, we're like really not that far advanced. I think we're already struggling to do things that are not hard gates, like fully random gates. So if you try to give them some structure, like you do Clifford gates like people do in numerics, this already makes the StatMech model a lot more complicated. So like, so in some way, like so we really like, going to your question, I don't think I have a good answer. So we have some kind of RG procedure to understand like this like transition. We don't understand a lot of it, I should say, right? So we don't have a good handle like for, except in this very large D limit that I mentioned. And we don't, you know, to what extent we can really say something quantitative for like changing the model entirely and getting rid of randomness. I think except relying on universality and hoping it works at this point, there's not a lot. So we certainly don't have a way, as what, you know, I have nothing like what you've mentioned, at least so far. But like I said, it's all been pretty recent, right? So.
Okay, and the final question is a bit funny. So if I understand correctly, the effective StatMech model, you're dealing again with the ground state. I mean,
yeah,
this
I mean, it's a StatMech model, right? So there's, it's a classical StatMech model. So I mean, there's, you know.
Yeah, so I'm just curious, what, I mean, if you now look at the excited states of that StatMech model, does it imply, I mean, do the properties of the excited states, or effectively, I guess, high temperature properties of the StatMech model, are they reflect? I mean, do they tell anything useful about the original model?
Yeah, that's a nice question. Yeah, so you can think of you can write a transfer matrix for that StatMech model, and then you can derive an equivalent quantum Hamiltonian. Well, I guess that's what you mean, right? And this was actually done by the same authors, like from Ehud Altman's group in Berkeley. They had a follow-up paper where they did this recently. And you can study those ground state Hamiltonians, which basically describe those transitions. And so the very high excited states, I don't know what to tell you, but the low energy excited states, you can do finite size scaling and they tell you a bit about like if you want the low energy spectrum of that conformal field theory, right? So they tell you about critical exponents and so on. If you think of high energy excited states of that system, I don't really know how they relate, to this, because here, like the free energy, like those entanglement entropies and so on, like in the thermodynamic limit, they only map to the ground state, like you say, right? So they only map to low energy excited states.
Okay.
So they would tell you about very strong finite size correct. Yeah, I'm not even sure. Yeah, I don't know if they have any physical meaning if you go deep in the. I think only the low energy spectrum here does really, unless you're doing small finite systems.
Okay, thanks.
Yeah, thanks.
Okay, we have a question also from Hyungjun. Hyungjun, please unmute yourself.
Hi. Thank you for a very nice talk. And I have two questions to be too specific. Anyway, I was wondering wondering what happened to the Renyi entropy other than the n equal to 2 in the entanglement transition.
Very good. Yeah. So all Renyi entropies map to the same statistical mechanics model, but they correspond to different things happening at the boundary. So it's something I haven't talked too much about, but I mentioned that like computing entanglement is like creating a domain wall. And so it turns out that which Renyi entropy you consider, it's a different type of domain wall, if you want. So here, of course, I had an Ising model, so there's only one type of domain wall, right? But you have to imagine it's a more complicated model which has many colors, if you want. And then the different Renyis are like different domain walls between different colors, if that makes sense. So really, it's like adding different boundary conditions along. So remember, the actual StatMech model has like a permutation group. So it's a very big group. It has many elements, and you can create many type of domain walls. And so the different Renyi entropies are like different domain walls. And so because of this, it tells you if you want like you still have the same transition, but like different, this free energy scaling could be a bit different because of the fact that the domain wall is different. So for example, the prefactor of this log at criticality is going to depend on which Renyi you look at in general.
Thank you. And the following question is, you're saying that the local, the entanglement entropy is in a local case. The capital A is the local area of capital A, and I guess there are a number of sites other than the single site in A local area of A. Then doesn't it depend on the size of the cluster of A, or?
So sorry, I'm not sure I fully understand the question. So like
the local, you measure the entanglement entropy in a local area of A, right?
I measure, I have like this finite interval A. That's what you mean, yeah?
Yeah. So doesn't it depend on the size of A? The number of sites. There are many
it depends on
number
which
of
phase you're
sites
in, right? Yeah. So like this free energy of a domain wall, like think of say an Ising model or anything like this, right? So if you create a domain wall like this, indeed, like in a ferromagnet, if you compute free energy of having the domain wall minus free energy of not having the domain wall, so really free energy of inserting the domain wall, right? That's going to scale with the number of sites in A. But actually, if you do the same with a paramagnet, it doesn't, right? So you can convince yourself if you take a paramagnet, it actually doesn't matter.
So the partitioning of the partitioning to get the entanglement entropy would depend on the would affect the entanglement entropy and the transition nature?
Yeah, so like whenever, like you can do all sorts of bipartition in that framework. And here that will change whenever you have a different boundary condition, right? So A will correspond to the region where you have a different boundary condition. And so you keep inserting those kind of domain walls.
Okay, thanks.
Thanks.
I have another probably short question, somehow related to the kind of comments that Alexei was doing. I mean, you said that somehow the model that you are considering is not an Hamiltonian because it's a random unitary circuit. Mm-hmm. However, you may probably think to go, let's say, as close as possible to an Hamiltonian situation by just, let's say, making randomness, let's say, on the first two layers, right, and then reproduce the layers. In that way, it will be a trotterization. Absolutely. Can you do that and you still have analytical control if you do this?
Yes. So yes, this I can say a bit more about. So this we may have a bit more control over. So this would give you a Floquet system, right? Because it would repeat in time. That's what you want, right? So you want like a periodically repeating pattern, right?
I don't know if a Floquet, or let's say you can think that you have an Hamiltonian done by, I mean, with the two layers, and you do a trotterization of that time.
Oh yeah. So I said Floquet just to think there was no small trotter. I mean, Hamiltonian would be on top of it. The gate should be close to identity because you're doing trotter, right?
Okay.
Right. Yeah. So I think in general the setup you said was Floquet, and indeed if you make all the gates close to identity, that would be like trotter because it would be like, that would be trotterization. So yeah, correct. So we can, this I think would be a way to go. It's a good point. So this would be a way to go towards the more general case. So I think the Floquet case, we can in principle do it. It's a bit more complicated already because there's a lot of things to average over. So basically so now the difference would be you have your circuit, but now it repeats in time, right? So it's not random in time anymore, it repeats.
Right.
And now when you want to average over a gate, you'll have more replicas if you want, because it tells you, like right now I had a gate and I had like different replicas and I had to average over this. But now I have like gates, the replicas, and the gate that will repeat in time afterwards, and all its replicas, and all those things are all the same. And they're all fully 100% correlated, right? Because they all have the same realization. And so now you want to average over all of this, which you can. Formally, it's going to give you like replicas that will scale with time in the system in some way. So this we thought a little bit about. We never wrote about it because I don't think we had anything very interesting to say. But like in principle, it can be done, like to think about this setup. Like if then you want to say it's like a trotterization, you need to put more constraints on what the gates are like.
Correct.
They have to be, So, and that would change a bit the family of the gate. But indeed, like you can see, that would be kind of a path to go towards, like, if you want
to say I mean, maybe you can see how much, let's say, robust are these universality claims while making more and more realistic the system.
So I think the first step is Floquet. People have done numerics on Floquet for sure. But here I think the StatMech model could still work, even though there are more subtleties with the StatMech model. And then you can think of modifying the family of gates, and I think that's the next step. You can also add conservation laws. So that's something we're doing now. For example, we're adding like U1 conservation laws or things so that it looks more like a typical system where you have a particle number or things like this. So those are things we are doing them now. Yeah.
Okay. Good. Thanks.
You can definitely add like at least those things one by one, at least, like I would say, just in, to go towards something that's maybe more Hamiltonian system with a bunch of conservation laws and so on. Yeah.
Right. Okay, thanks.
Okay, do we have any other questions from the audience? So it seems not. So let us then thank Professor Vasseur again.
Thanks again, everyone.
And with this,